Somewhere in a repair shop in Flagstaff, Arizona, a retired schoolteacher is staring at an invoice for $6,400. The car on the lift behind the service counter is her 2009 Toyota Camry. The car she bought new, the car she has maintained without exception for 15 years, the car whose oil she changed every 5,000 miles with full synthetic eye, whose coolant she flushed on schedule, whose transmission fluid she replaced twice before most owners had considered it once. The car she did everything right with. The invoice in her hand is for a partial engine rebuild, new rod bearings, resurfaced crankshaft journals, oil pump replacement, and the labor to access all of it. The mechanic who wrote the invoice is a 20-year veteran who has seen this specific failure pattern enough times that he recognized it within the first hour of teardown. He is now trying to explain to a woman who followed every maintenance guideline her dealer ever gave her that her engine sustained the kind of internal wear damage that typically takes decades of neglect to produce, and that the entire chain of destruction traces back to a single component that costs between $8 and $12 at any auto parts store in the country. The part is the PCV valve, and if you own a Toyota, any year, any engine configuration, what follows is the most important 10 minutes you will spend on your car this year. Most owners have heard the term PCV valve without ever fully understanding what it does or why its failure carries consequences so disproportionate to its size and cost that the relationship between the two feels almost implausible. That gap between familiarity and understanding is precisely where this failure lives. Owners who know the name but not the function treat the PCV valve the way most people treat the spare tire. They're aware it exists somewhere in the car. They have a vague sense that it matters, and they give it no further thought until something goes wrong. By the time something goes wrong with a PCV valve in the specific failure pattern that destroys Toyota engines, the damage is already done. The valve itself costs $10. The consequences of its failure on a Toyota engine that was otherwise perfectly maintained can cost between $3,000 and $8,000 depending on how long the failure went undetected and how hard the engine was driven during that window. Understanding why requires understanding what the valve actually does, not at the surface level of its name, but at the level of the specific problem it was engineered to solve, and what happens inside an engine when that problem goes unsolved. Every internal combustion engine produces blow-by. This is not a defect. It is a physical inevitability. During the compression and combustion strokes, a small percentage of combustion gases, hot, pressurized, chemically aggressive gases containing unburned fuel, water vapor, acids, and carbon compounds, escape past the piston rings and enter the crankcase. The crankcase is the lower section of the engine block where the crankshaft lives, where the oil lives, where the bearing surfaces that connect the rotating assembly to the block are continuously bathed in pressurized lubrication. In the earliest internal combustion engines, blow-by gases were simply vented to atmosphere through a road draft tube, a pipe that used the vehicle's forward motion to create a pressure differential that drew crankcase gases out and dumped them into the air behind the car. The environmental consequences of this approach are obvious in hindsight. The engineering consequence that wasn't immediately obvious is that venting blow-by gases freely also vented the oil vapor they carried, gradually depleting the crankcase of lubrication and depositing an oily film on every road surface the vehicle traveled. The positive crankcase ventilation system, introduced progressively across the industry beginning in the early 1960s and mandated on all American market vehicles by 1968, solved both problems simultaneously. Instead of venting blow-by gases to atmosphere, the PCV system routes them back into the intake manifold through a metered valve, the PCV valve, where they are drawn into the combustion chamber and burned with the normal air-fuel mixture. The crankcase stays sealed, the oil vapor stays in the engine, the combustion gases get consumed rather than released. The PCV valve meters the flow of those gases precisely enough that the crankcase maintains a slight negative pressure, a gentle vacuum, that keeps the seals loaded correctly and prevents oil from being pushed past gaskets and out of the engine. That metering function is everything. The PCV valve is not a simple on-off valve. It is a spring-loaded, flow-regulating device that modulates the volume of crankcase gases entering the intake based on the pressure differential between the crankcase and the intake manifold, a differential that changes constantly with engine load, RPM, and throttle position. At idle, intake manifold vacuum is high, and the valve partially closes to prevent excessive flow that would lean out the idle mixture. Under hard acceleration, manifold vacuum drops, and the valve opens more fully to handle the increased blow-by that high load combustion generates. It is a continuously variable component performing a precision function in an environment of heat, oil vapor, combustion byproducts, and constant pressure cycling, every minute the engine runs. Toyota's PCV valve design across their major engine families. The 2AZ FE 4-cylinder in the Camry and RAV4, the 2GR FE V6 in the Camry, Avalon and Highlander, The 1GR FE V6 in the 4Runner and Tacoma, the 3UR FE V8 in the Tundra and Sequoia, uses a straightforward spring and plunger mechanism inside a plastic or metal housing that threads or press fits into the valve cover. The design is reliable, the materials are appropriate for the operating environment, and the service life of the component, under normal operating conditions with regular oil changes, typically runs between 40,000 and 60,000 miles before the spring tension degrades enough to affect flow regulation meaningfully. Toyota's official maintenance schedules across most of their platforms list the PCV valve as an inspect item at 60,000 miles and a replace item at 90,000 miles in severe service conditions. In normal service, many schedules don't list a specific replacement interval at all. It appears, under the general inspection category, that most owners and many shops treat as a visual walkthrough rather than a functional test. This is where the failure begins, not in the valve itself failing dramatically, in the valve failing gradually, silently, in a way that produces no warning light, no obvious symptom, and no indication visible during a routine oil change or multi-point inspection that anything has changed. The spring inside the PCV valve weakens over time and with thermal cycling. As it weakens, the valve's ability to modulate flow correctly diminishes. The two failure modes that emerge from spring degradation move in opposite directions and produce opposite consequences, and understanding both is essential to understanding why this single component can destroy an engine from two completely different directions. The first failure mode is a valve that sticks open, a valve whose weakened spring can no longer close the plunger against high intake vacuum, allowing the full crankcase pressure differential to pull excessive blow-by gas volume into the intake manifold continuously, including at idle, when the flow should be restricted. An open PCV valve floods the intake manifold with oil vapor at a rate the combustion system wasn't designed to handle. The immediate symptoms are subtle: a slightly rough, idle, elevated hydrocarbon readings, occasional blue-tinted exhaust on cold starts that clears quickly. The longer-term consequence is systematic carbon accumulation on the intake valves and combustion chamber surfaces from the constant stream of oil vapor being burned with every combustion event. On Toyota's direct injection engines, the D4S system used in post-2012 platforms. This accelerates the intake valve carbon accumulation that is already a known consequence of direct injection architecture, compressing a problem that typically develops over 100,000 miles into a timeline that can produce operationally significant restriction in 40,000 to 50,000 miles on an engine with a failed open PCV valve. The carbon accumulation causes the misfires, the hesitation, the elevated fuel trims that get misdiagnosed as injector failures and sensor faults, while the actual cause continues operating and continues accelerating the damage. The second failure mode is the one that generates the $6,400 invoices. It is the failure mode that destroys bearings on well-maintained engines, with clean oil and correct change intervals. And it is the failure mode that the retired school teacher in Flagstaff encountered without any warning that it was coming. A PCV valve that sticks closed, whose plunger has become gummed with oil varnish deposits, or whose spring has collapsed under prolonged heat exposure, stops venting crankcase pressure entirely. The blow-by gases that every engine continuously produces have nowhere to go. Crankcase pressure builds. It builds slowly at first, imperceptibly, in a way that produces no warning light because there is no sensor monitoring crankcase pressure on most production vehicles. As pressure builds, it works against every seal and gasket in the lower engine. The rear main seal, the circular seal around the back of the crankshaft where it exits the block toward the transmission, begins to seep. The valve cover gasket begins to weep at its corners. The oil pan gasket develops a slow drip. These are the visible symptoms that attentive owners notice first, and they are almost universally misread as normal high-mileage seal wear, rather than active pressurization damage. Most shops replace the seeping seals without testing the PCV system that is causing them to seep, which means the new seals encounter the same elevated crankcase pressure the old ones failed under and begin seeping again within 20,000 to 30,000 miles. But the seal failures are not the catastrophic outcome. They are the warning that almost nobody interprets correctly. The catastrophic outcome happens inside the engine, out of sight in the bearing clearances, where the crankshaft rides on its film of pressurized oil. Elevated crankcase pressure in a sealed engine creates a back pressure condition that works directly against the oil pump's output. The oil pump on every Toyota engine is a positive displacement device. It moves a fixed volume of oil per revolution regardless of the pressure it is working against. But the pressure differential between the pump output and the crankcase affects the net pressure available at the bearing surfaces. When crankcase pressure rises due to a failed closed PCV valve, the effective oil pressure at the rod and main bearings, the bearings that support the crankshaft through every combustion event, decreases by a corresponding amount. This reduction is not dramatic in any single moment. It is cumulative. It compounds across every mile driven with the valve stuck closed, gradually reducing the oil film thickness at the bearing surfaces, gradually increasing the metal-to-metal contact that the oil film is designed to prevent, gradually accelerating the wear that opens up bearing clearances beyond their design tolerance. The insidious element of this failure sequence is that the oil pressure gauge on the instrument cluster, present on some Toyota platforms, absent on others, does not reflect this reduction accurately. The gauge reads system pressure at the main oil gallery, upstream of the bearings, before the back pressure effect reduces net pressure at the bearing surfaces themselves. An engine with a failed closed PCV valve and active bearing damage from reduced net oil pressure can show a normal oil pressure reading on the gauge, while the rod bearings are experiencing a wear rate 10 times higher than normal. The owner sees a normal gauge reading and concludes the engine is fine. The engine is not fine, the engine is consuming its rod bearings at a rate that will produce the characteristic rumbling knock of bearing failure in somewhere between 15,000 and 40,000 miles, depending on how far the clearances have already opened and how hard the engine is being driven. This is precisely what happened to the Camry in Flagstaff. The PCV valve had stuck closed at some point around 140,000 miles. A valve that should have been replaced at 90,000 miles and wasn't, not because the owner was negligent, but because nothing in her maintenance schedule had flagged it specifically, and no shop she visited in 50,000 miles of servicing had tested its function. The crankcase pressure buildup that followed had been slowly working against her rod bearings for the better part of 2 years. The rear main seal had begun seeping at around 155,000 miles. She noticed the small oil spot on her garage floor and had the seal replaced at a cost of $380. The shop that replaced the seal did not test the PCV valve. The new seal seeping again 6 months later should have been the signal. It wasn't recognized as 1.02 inches. The 30-second knock on cold start was the bearing running metal on metal until oil pressure built enough to float the journal on a film that the clearance had become too wide to maintain reliably. Within 3 months, the knock had extended to 45 seconds, then to a minute, then to the point where it was present throughout cold operation. By the time the car reached the shop that correctly diagnosed it, the rod bearing on cylinder 2 had spun, rotated in its housing under the heat and pressure of a lubrication failure, and scored. The crankshaft journal in a pattern that required professional resurfacing to save the crank from complete replacement. The PCV valve that caused all of it was removed during teardown and tested on a bench. It produced zero flow at any pressure differential. It had been completely sealed for an estimated 25,000 to 30,000 miles. It weighed less than 2 ounces. It cost $9.47 at the parts counter. The prevention protocol is straightforward, takes less than 2 minutes, and can be performed by any owner in any driveway without tools beyond what is already in the factory toolkit that came with the car. Locate the PCV valve on the 2AZFE 4-cylinder, on the engine in the 2002 through 2011 Camrys, and the 2006 through 2012 RAV4. It is located on the valve cover toward the rear of the engine, connected to a rubber hose that runs to the intake manifold. It either threads into the valve cover or press fits into a grommet depending on the model year. On the 2GR-FE V6, the Camry V6, Avalon, and Highlander, there are 2 PCV valves, one on each bank's valve cover, both connected to hoses running to the intake. On the 1GR-FE V6 in the 4Runner in Tacoma, the valve is on the driver's side valve cover near the firewall. With the engine at idle and fully warm to operating temperature, disconnect the hose from the PCV valve without removing the valve from the cover. Place your thumb firmly over the open end of the hose. You should feel a distinct, steady vacuum pull against your thumb, strong enough that removing your thumb causes a noticeable hiss of air entering the hose. This vacuum confirms that the intake manifold is pulling crankcase gases through the valve correctly and that the valve is open and flowing. If you feel no vacuum, or a very weak intermittent flutter rather than a steady pull, the valve is restricted or closed and needs immediate replacement. Next, remove the PCV valve from the valve cover and shake it next to your ear. A functioning PCV valve produces a clear, light rattling sound as the spring-loaded plunger moves freely inside the housing. A valve that has been gummed by oil varnish or whose spring has collapsed produces either no sound or a dull, dampened sound without the clear rattle. No rattle means no function. Replace it immediately. The replacement itself is a 2-minute procedure. Remove the old valve, thread it or press fit depending on the platform, and install the new one. Toyota. Genuine PCV valves cost between $8 and $14 depending on the engine. Aftermarket equivalents. Meeting OEM specifications are available for less. The hose that connects the PCV valve to the intake manifold should be inspected simultaneously. These hoses crack and collapse on the inside in a way that restricts flow without any visible external damage. And a new PCV valve behind a collapsed hose produces the same crankcase pressure buildup as a failed valve. Squeeze the hose along its length. It should be firm and resilient without any soft spots or internal resistance. If it collapses under moderate finger pressure or feels brittle and stiff, replace it alongside the valve. The hose typically costs between $12 and $25. The replacement interval that prevents this failure entirely is simple. Every 40,000 miles or every 3 years, whichever comes first, replace the PCV valve on any Toyota engine regardless of what the maintenance schedule recommends and regardless of what the functional test shows. At $10 a valve, replacing it preventively every 40,000 miles costs less than a single quart of the synthetic oil the engine already requires. It costs less than the diagnostic fee the shop will charge to tell you why your rear main seal is seeping again. It costs less than 1% of the bearing repair it prevents. The math requires no elaboration. What this one component reveals about Toyota maintenance, and about the maintenance of any complex mechanical system, is something that service schedules and dealer checklists consistently fail to communicate. Not every critical component announces its failure loudly. Not every part that can destroy an engine costs hundreds of dollars, or requires specialized knowledge to inspect. Some of the most consequential failures in automotive history have traced back to components so inexpensive and so accessible that their failure seems almost embarrassing in retrospect. The PCV valve belongs to that category. It lives in plain sight on every Toyota engine built in the last 30 years. It requires no tools to test and less than 5 minutes to replace. And it has destroyed more otherwise perfectly maintained engines than any sensor failure, any gasket leak, or any cooling system event that owners spend far more time worrying about. The school teacher in Flagstaff drives a different car now. The Camry was repaired, the bearings replaced, the crank resurfaced, the rear main seal renewed for the second time, this time with a new PCV valve and hose installed before the engine was closed up. She drives it still. It has 31,000 miles on the rebuilt lower end and runs without a trace of the knock that nearly ended it. She checks the PCV valve every oil change now. Takes 30 seconds. Costs nothing. She will not be making that phone call again. Neither will you. Go find where your PCV valve lives. Shake it. Feel the vacuum. If the rattle is gone or the vacuum is weak, spend $10 before the engine spends that decision for you at a cost you won't forget. That is the entire distance between a $10 part and a $6,000 lesson. 90 seconds, and the willingness to check the thing that nobody told you to check until it was too late. Check it today.